Good evening, folks. Welcome back to Expat Audio. We're live streaming right now. Let me make sure we turn this down just a little. There we go. Yeah, what you're looking at right now is the VU meter board with no filtering going on at the moment, but it's working its way. I've got music playing from Winamp into it, and it's all working. I'm very happy. And today's topic, let me just PowerPoint here. Reading view. Today's topic really is how on earth do I get into production? And now that I've actually finished my prototype, and I'm fairly confident, I'm very confident in the software that I've written for it. And so, all right, so prototype's done. What do I need to really go into manufacturing? And when I say manufacturing and releasing a product, it's no longer just about, can I make a bunch of PCBs? There's a whole process that really needs to go into place so that, regardless of when I do the batches, whether I do a batch every month or whether I do a batch every 12 months, that there's consistency in the product that I'm releasing. It's really important. There's a lot of tricks here that I've learned from my daytime job at TI, but I think if you guys are looking into doing your own open source hardware or even releasing your own stuff, or even just looking to building batches for some stuff that you're doing for your own use, it's good to have some of these practices. So the prototype's done. Now what? We need to generate the files for manufacturing, the bill of materials, so that we understand not only what parts do we need to order and stuff, but what our cost structure truly is versus what it was when we started. There's a big difference. The firmware files need to be locked down and put in a safe place. A test program needs to be developed so that you can consistently put out high quality hardware, and even things like the packaging details. So the manufacturing process, as far as I'm concerned, is you've got to have the PCBs manufactured. You've got to do your surface mount devices pick and place, and that's very important. And again, you got to do some reflow those, make sure they're on the board and soldered. Then we do our dip insertion. Dip is typically called dual inline packaging, but it basically means any through-hole components that you have need to be manually inserted most of the time. There are some machines that can do dip insertion, but because things like legs on resistors, the legs on through-hole, the ICs and so on, tend to be not the easiest to plug in and so on. It's often easier to get a human being to do that. We need to program the board, so often if you have a microcontroller of some kind, or if you have an MCU running, you definitely need to be able to program it. And then once you've programmed it, you've got to test it to make sure that everything's soldered correctly, that all the components are working within specification and so on. And once that's all done, packaging it up in a consistent manner so that your shipping company that you use, unless you're shipping yourself, knows exactly what to do. And so let's walk through these really quickly, and then I'll actually walk into what we're doing for the tiny VU. From a PCB manufacturing perspective, you need to create panelized Gerber files. So what you can see down here in the let me make sure there's no questions or anything, sorry. In this graphic here is I actually took the tiny VU and stamped it 4 times. And then I also have a little bit on the side here and here so that it can slide into my pick and place machine quite easily. There's also things like fiducials on the board. Fiducials are special marks which help you align the circuit board and so on. Now what you see in the background are some of the images here of these are from PCB Pool, a company in Europe that does PCBs. They do large sheets of them and then they route them out. So you can have either these lines between each of the boards scored, so that there's like a V in the PCB, and you can snap them once they're manufactured, or you can have them actually routed, where there's actually like a drill bit, or like a milling bit that goes through and cuts out the boards. And so one thing I was going to add is that 2-layer boards are much cheaper than 4-layer boards. However, 9 times out of 10, the 4-layer boards are more likely to work. In fact, the trend I've seen with a lot of companies that I work with, my day job, is for their first boards, just to make sure that the software is working and the layout works and everything, they'll do a 4-layer board, and that means 4 layers of copper separated by insulators so that you can have 2 signal layers and then like a ground and a power supply layer. It just makes things much more reliable, much easier, but you do pay for it on the other side. And the other thing I was going to mention is much easier to manufacture in panels like this, where you have 4 on a board, than it is to do with singles. The pick and place machine wants, it's optimized so that the busier you keep it. So for instance, if one of these boards takes, I don't know, 3 minutes to populate with all the components, 4 of them does not take 12 minutes. It's closer to like 9, because there's less swap out time and recalibration time and so on. All right, so let's carry on here. For the pick and place machine, we need a centroid file for device location. So Eagle or Altium or anything like that will give you this file called a centroid file. It says resistor number 1 goes at location X 1.115 millimeters and Y 2.45 millimeters and so on. And so it helps know, it tells your pick and place machine where everything goes. But before you put your boards in your pick and place machine, you have to apply solder paste. Solder paste is, trying to think what it's almost the same consistency as a thick yogurt. I can't think of a better way of describing it. But essentially, it's used it's basically flux with very small balls of metal in it, and when it gets very hot, it flows and creates a solder joint for you. So it's typically you'll use either a little dispensing gun, for lack of a better term, to drop bits of solder paste, or the really nice and easy way is to use a screen. So if you've ever made t-shirts, a silk screen where you have a mask, and there's holes where you want the paint to go through. It's the same with solder paste. You pop that down, and then you squeegee through solder paste as you need it, and then that'll go onto the pick and place machine, and from there the parts will be put down. You do a quick optical inspection to make sure everything looks okay, and then you'll put it in a reflow oven. And that's what this long thing is here. There's a conveyor belt that goes through here, and inside is very hot and with different temperature zones, and so it'll actually warm up the solder paste with the correct profile so that the flux burns off, if you will, and helps everything move into place, and then the little metal balls which are in the mix melt and melt appropriately. Now, one of the things I was going to try and show you guys here is there's actually I have a video of the pick and place machine that we have at Expat Audio. Let me see if I can find that. Expat Audio pick and place YouTube. Let's see what comes up. Okay. See if I can shrink this. Maybe I can move this over. Okay, so we're just going to get the pick and place up and running. Means I have to align the fiducials, which I do by looking at this monitor. Can't see it very well, maybe it's a little bit too bright. Basically realign the 2 fiducials. At which point it starts looking. So one of the things I wanted to mention here is that this is actually an early prototype board for the Expat Audio Eden microphone preamplifier, and you can see here this is a single board. So you can see, you saw how long it took me to calibrate and get the the alignment points, the fiducials ready. Once you're doing 4 boards, for instance, then you only have to do that once. Then, in addition, if I wanted to go, I can go further out and further down. However, it gets harder then because maintaining accuracy over a longer distance from the origin, the 0 point, becomes harder as well. Now, on my pick and place machine, by there, it's an ECM 93, an old Mancorp machine. It runs MS-DOS still. on the machine that I have there, it requires optical teaching, so it uses the camera to teach the system where each part is. So that won't use a centroid file, but the modern systems, even like these Chinese built ones, you give it an Excel file and it picks up the part locations, and again you tell it where to pick up parts from, and it just, for lack of a better term, runs itself. Okay, so let's carry on a little bit here. Dip insertion. So the professionals will use a conveyor belt like this, and they'll have operators that will manually place the components in the right place. And the way they do it, they typically have diagrams, in front of them. So each operator will have like a piece of paper printed out in front of them, and that piece of paper will have, box number 1, which has maybe 1K resistors. That goes here, 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 and here on your PCB. However, the real pros who have done this for a long, long time, they actually have pick-to-light systems. And what that means is they have something that looks like a projector shining down from above that shines on the PCB and shows, hey, when you're putting in component number 3, component number 3 needs to go in here, and it'll light up a specific part of the PCB. It means the PCB needs a jig to sit into, but it's a really cool way of, highlighting to operators exactly where the parts go. And doing things like that help lower that human error. But really, you can definitely get a wrong resistor in the wrong place error. And from there, if you're building in small quantities, if you're a single man operation or 2-person operation, you're building, tens at a time, then you might be able to solder those yourself. Simply put them in, flip the board, and grab your manual soldering iron, solder them, and then snip them. But what's pretty common in volumes which are higher, so 1,000 boards or more, is using what we call a wave soldering iron. And here, what you have is a bath and a wave of hot solder and a conveyor belt. The boards go down on the conveyor belt, and they pass over. They pass over the wave, and from there, get soldered down and so on. All right. Now, once you've done that, you've got to program this darn thing. So, our tiny VU board. Let's have a quick look. Our tiny VU board has I'm not sure if I show this properly, a real microcontroller on there. And that microcontroller needs code. It needs to be downloaded from it. And so what you end up needing is some kind of programming hardware, which is your programming hardware. You'll need some kind of programming hardware that connects on a special connector to your circuit board, so that when you plug it in on your factory PC, if you will, it simply, with one button, will download the firmware. And that's actually a nice way of knowing that your part of your manufacturing flow has gone well if this programmer can find your chip on there and say, hey, I can talk to it and I can download to it. So that's a good job, right? Power supplies, for instance, are working, and soldering has gone pretty well, at least for the pins that carry that. Now, you typically have dedicated pins to do this, and one of the tricks behind doing this is to use special connectors so that they're as small as possible, because your programming header is only truly used once you're in production. So you don't want to dedicate like a big 14-pin connector for it and waste PCB space. If it's only something that's in the corner, then you could probably use like a 4, 5, or 6-pin, very, very tight header, and that's what this is here. Now, to actually program it, you can buy a dedicated header, or you can cheat a little bit. And this is what I'm doing with the MSP430 here. This is the launch pad. This is their eval kit. And normally, this board talks to the chip that's on the board, so that you can make an LED flash and so on, a little bit like an Arduino. But what this user has done here, and I'll put a link to his post a little later, is he's actually hacked into it a little bit and brought those connectors out to a breakout board, which can then go to something like this and program the board. So it's very, very nice. These launchpad boards are $10 these days from TI, and when they're trying to do a special offer, it's $4.30, right? Just to be quirky. And you can actually see in our development kit here. Let me jump back to the full screen. You can actually see. Come back That's exactly what I've got going on here. Okay, so you know, it's a little bit more wiry, a little bit more messy because this is a prototype in the development board, but essentially I'm bringing VCC, so 3.3 volt ground, and then some of the debugging lines over to the board. And the nice thing about these boards, and it's the same for Arduino, there's also a serial port and you know, a UART that comes over from your PC, so that if you do some kind of let me see if I can bring this up here. If you do some kind of interface for the product, it's going to work for me. No, it doesn't want to work for me today. It's worth a try. If you do want to, you know, have a test mode that you can go into and just press a couple of buttons to run software on the device, like switch on all LEDs, right? You can use the serial port to COM in to the product and you know, set it up appropriately. Very, very, very convenient for that. All right, so typically you'll have a dedicated jig, and that, you know, that's what we mean by this. Now, once you move on to testing the product, you know, the pros use a bed of nails tester. This is, you know, like a pro solution. This is the this is a one off eBay that you can get, where you know, you'll send your design to them, and they'll use a bed of nails. These are pogo pins, or nails as they might be known. And the pogo pins, what they do, they're a metal conductor, and they have a spring on them, so you can push down with your board and they'll guarantee a good connection. And so what people typically do is very similar to this SparkFun board, which is they'll use little tabs to hold down the board onto these pins, so there's always a good connection. And at which point those pins can be routed off to, you know, your bench hardware, like a power supply, a multimeter, a signal generator, and so on. And you'll run through each tests to test each part of the hardware there using standard instruments. And typically you'll have like a document that's got, like, you know, first thing to do is test the power supply and how much current is it pulling. Second thing to do is to make sure that your, you know, your front end on the tiny view, you know, you would check that the signal chain before the microcontroller is functioning well. And so, you know, it's a full bridge wave rectifier, so I might have a sine wave generated by a piece of hardware, and then an oscilloscope to make sure that it's a non-distorted, a full rectified wave, and so on. So we can do things like that with these boards. I also really like the idea of using like an Arduino or something to communicate with the PC, and using the Arduino's onboard hardware, you know, to generate sine waves, to generate and to be able to measure GPIOs and so on, just so you can log on your PC, you know, what each board that you made did. So if, let's say, let's say for instance, on each circuit board you had, you put on a serial number for every board, then you could have, for instance, your Arduino poll the board to say, hey, what's your serial number? And you get your serial number, and then you could actually log each of the values coming back from the board. So, you know, if you put in 1 volt, what's coming back out? Is it 1.1 or 0.9? And log it then, so that if you ever get any returns, you can see very quickly what could have caused that return, and have a look for consistent failures in your test. So pretty nice way of doing it. There's an excellent tutorial over at SparkFun on this. If you Google for innovation in quality control, it really is. These guys are experts at this. They've built millions of boards by now, and truly, you know, they test all of them. You know, this jig up here is, for example, one of them. The green PCB here is the actual test PCB, and then what you see underneath is the device under test. And then there's the boring stuff. So at Expat Audio, I don't ship anything anymore. I used to do all the shipping for it, and you know, if I was lucky because of my job during the day, I was too tired, busy when I got home at night, you know, things would ship out every 2 or 3 weeks, and customers would be waiting. So I found a fulfillment company here in Dallas, a company called Megatronic, that does it for me, and they you know, they get a list of things for me. They get, you know, bagged up boards already, and then they get a barcode for everyone, and they get a link into the online store. And then as soon as an order is made, they get an email saying, hey, you know, an order was made at Expat Audio. These are the parts required with a barcode, and this is where it's going to. And then they can go into their picking room, you know, get the appropriate size cardboard box that's been specified, and they go 1, 2, 3, 4, or, you know, padded envelope if they're just PCBs, pack them up, ship them on their way. But, you know, the important thing here is that, you know, I may only be building certain batches of products once every 3 or 4 months. And to make sure that there's consistency, it's a really great idea to, you know, as you build up your first batch, you know, make a list of the size of the ESD bag, where you're buying them from, the cost, very, very important, of that. Same for the cardboard box, the filler, so that next time you do a batch, you can, you know, you can really execute in real time and do a good job of, you know, consistency for the end customer. And that comes down to everything that goes into the box. So, you know, the ESD bags, the cardboard box, the filler, any manuals you want to put in there, you know, understanding what the ship weight is. So, you know, you need to add it all together, put it on the weighing scales, and you'll say, okay, this is, I don't know, 0.3 pounds or something like that. Well, then you need to understand, does that fit in, you know, how much is that going to cost to send domestically? And in the US, there's a fixed shipping rate that we just use. But, you know, for international, the costs can vary widely. And the other thing is you need to get a barcode as well. And you can actually buy barcodes online. So I'll give you an example here. Buy barcode. There we go. There's one here I've used before. I'm picking one at random now. But for, you know, about $5 to $10 per barcode, you can get an official barcode, which actually allows you to sell through Amazon as well. Now, we haven't gone that far yet because a lot of our business comes direct to Expat Audio, or it goes to, you know, ships to Europe, and Amazon doesn't really like shipping to Europe from the US because of customs and all that kind of thing. But this is a great way of, you know, getting legit for your product. Now, these guys, that's crazy, $75. There are cheaper ways, believe me, but keep Googling. You can typically buy like 10 of them for $20 or something. Very, very easy to use. All right, let's just jump back to this. All right, so you've now, let's jump back and I'll introduce the next section. So you've now, okay, you've got your PCBs manufactured. You've built, let's say, 100 PCBs. You've pushed them through the surface mount pick and place and reflow, and dip insertion programming, and you've tested them, and, you know, let's say you fixed any production problems along the way. So for instance, let's say you have one of your resistors isn't being placed properly every time on your boards, then you should have gone back, fixed that, so that your yield at test should be at least 90 to 95%. So, you know, in the ideal world, once, you know, 90%, 9 out of every 10 of the boards you manufacture should just fly through the test process, and maybe one of them goes back, you know, for rework. So, you know, back in, it goes, oh, you know, it's actually didn't get this resistor or whatever, solder it and fix it. Because, you know, if you do have to throw away some of those boards when you're done with them, it gets very expensive very quickly. You know, if you have a 50% yield, and let's say your board costs $10 to make, well, actually, the true cost once you sell it to the customer is now 20, because you've taken one and just thrown it away in the trash. Unless you want to work extra hard and spend your time equals money, you know, to fix that board and so on. So get your yields up before you release the product. That's actually one of the big pieces of homework I have with this board. So once you've done all of that, you know, you need to qualify your production line. I suggest you build 100 units, ship them to beta testers, ship 3 of them to yourself. And, you know, just double check, you know, do your boards work? How hard were they to get up and running? And, you know, bring back in any boards that have failed and do an analysis on why did they fail. You know, in some cases, it could be something as simple as tall electrolytic capacitors got bumped in shipping. And they get bumped every time you do shipping because you didn't specify a cardboard box that was big enough with enough padding, for instance. So it's really worth doing that little bit of extra homework. It can delay you going to release for maybe a month or so, but I think it's definitely worth taking time to make sure that they work correctly. All right, let's walk through what we did for the tiny VU. So I think in last week's show I actually showed what we did with the panelization and so on, and then what I did to make a test board was I actually want a board that can plug in to one of these MSP430 launchpad boards, so that I get power from it, I get programming, and I get a serial port just by plugging this thing in like an Arduino Shield or a cape or whatever. And the one thing I have to do, I'll have to remove this chip, but as soon as I plug it in, I should get access and be able to program these other boards. All right, so let me just jump back to Eagle here. All right, so what you see here, these two long pads here, these M10, are the two pin headers on the sides of the board. And what I'm actually bringing up from them is 3.3 volts, ground, serial port, and the programming header for the MSP430. All right, and I've got a little bit of decoupling, just in case. This little circuit here is a big pot, along with the capability to bring in a true analog signal, an audio analog signal, and switch between them with a switch, so that if I want to test thresholds or making sure that all of the LEDs are working, I can simply put it into the pot mode and swing between ground and 3.3 volts. Just turn the pot, and you'll see it, and you'll see the LEDs climb and fall again. And that using a DC input to this board won't typically test the full wave precision rectifier very well. For that, we'll actually use the audio input as well. Okay. If I want to go out of the board to make sure that other boards are working, I've got extra headers here for my UART, which is the these actually connect. These are the pogo pinholes for the UART side of the board and the SPI-by wire. SPI-by wire is what's used to program the MSP430. All right. I've got similar things going on here. This is actually the array of LEDs, let's have a look if I can show you guys the board real quick. Here we go. So here's a cut down version of the tiny VU. So here's the programming header that we have. And over here is the serial port header. Once you're building it in your system, you'll only use this connector. You'll give it 3.3 volts, ground, and then the serial port connectors. Now, in your application, typically this is scored, and you'll snap this off so that this tiny board here sits on your front panel, and then this sits a little further behind, and you'll run wire between each of these points at 1 to 2, 3 to 4, 5 to 6. What we do on the test board is I have a whole array of pogo pins here and a whole array of pogo pins there, so that the signal from the MCU, which is now pushed onto this board, goes in there, down to the test board, across and back up to light up the LED. Very, very simple in that respect. And then one thing I learned from some of the old TI boards is I've got a huge array of just holes here that if I need to make an extra little bit of circuitry or something, I can do some through-hole stuff just over there to help fix the board, or bypass something, or anything else like that. If I need an extra power supply, I could just do it there with some through-hole parts. These holes here represent some of the holes on the final daughter card that plugs in, and they also represent headers that can, standoffs that can come up to be used to hold the board down. And so let me show you what I'm talking about here. This is the SparkFun page. Just scrolling through here to see if they have something along these lines. Okay, so for instance, this is a very, very small tester that they have, and the board under test will actually fit in here. It's tiny, but they need all these extra screws around to make sure that everything else can hold it in place and so on. So you can see their board, they'll just plug it in by there. They turn these little bits of extra PCB on there, and it holds down the board against the pogo pins. Let me see if they have a photograph of pogo pins here. You can see the pogo pins up here. They're using, they're soldered into a bottom board and plug straight up. So let's go back to our board, the schematic. I think there's anything else to show you on the schematic. It's very simple. It's based on the form factor of the launch pad itself, the MSP430 launch pad, so that it can just plug in and bring signals up. And if we look at the layout, again, really, really simple. These pins here down this side and this side are launch pad pins. So they will have a downward facing female connector. These are the pogo pins for the LED array. These are your programming pins, and then this is simply to either test DC inputs or to take an analog audio input from an external source. In fact, I could change it for a 3.5mm jack, like a headphone socket, and bring it in that way as well. And then I can use this switch then to switch between them to see if the board is working. Doing it this way, along with using the serial UART stream to switch it into different modes and things, helps me test these boards very, very quickly. So the faster my test, the faster my production. And this is something you really have to consider. So say, for instance, it takes you on average 10 minutes to build a board. Now, if you assume somebody is building for you, let's say you've hired someone with a little bit of brains on their shoulders to do the manufacturing for you. You could be paying them $10, $15, $20 an hour because you're only hiring them for an hour or two monthly in some cases, right? Or an hour or two a week. So you can't just give them McDonald's salaries, right? They should be smart people. You want to be able to crunch through as many of these boards as possible, and we simply take how many boards can you do in an hour divided by your hourly salary, and that gives you an idea of how much extra it costs you to test the boards. So your final test, your final cost of build of a product is going to be a PCB cost, component cost, pick and place time. How long did it take to pick and place, and with you sitting on there watching it, making sure it works okay. Test time, rework time, packaging time, and so all this really adds up very, very quickly. And frankly, it's pretty obvious that this is a passion of mine. That's the only way I think I could make it work. But there we go. So these boards will be sent off soon to be manufactured, and we should get them back in the next 2 to 3 weeks. And in the meantime, I have to write the test program and all the rest of it that goes into this product. So I just see a question here from Sean Taylor. I'm sorry, Sean. It's on the Facebook thread here. Sean was saying, "What's a tiny VU?" I'm sorry I didn't see this sooner. I was too busy rambling here. A tiny VU is this board that you see down here. So this is actually 2 of them from a panel that I had manufactured, and it's used as a VU meter, a volume unit meter. So you can be, let's say you are in the studio, you've got your mic pre-set up, and you want to see in real time how loud the signal is coming in or how loud the signal is going out. And you want to make sure that you're not going to clip your audio interface and so on, but you want to be doing it in real time and not finding out after it's been recorded by looking at the meters in your digital audio workstation. So by watching a board like this, seeing how these LEDs are flying back and forth, you can get an idea of what the peak power is, what the average power is, and what the instantaneous power is very, very, very quickly. I hope that answers your question. I will actually jump on to the thread after I'm finished here and reply to you in thread as well. And that's it for tonight, I think. We've been about half an hour here, I think. So I'm going to sign off at this point. But thank you very, very much for tuning in. Next week we'll talk a little bit more about the actual test program, how we're going to do it, what we're going to do it, and maybe some of the calibration that needs to be done. And we'll take it from there. And if you have any requests or questions to do with bringing a product to production like this or any of the other Expat Audio products, please tune in to Expat Audio on Facebook. You can ask your questions there, ask on the YouTube pages for these videos, and we'll take it from there. All right, folks, thank you very much. I appreciate it. Have yourselves a good evening.